In this video, we would understand how do we solve the numerical and find out what is the power factor with respect to generation based on the given set of parameters. So I'm Mohan BS, working as Assistant Professor, Department of Ripley, SJBIT. So in this problem, transmission system as shown below, having all in per unit system, voltage base and taken the apparent power as the base SB is 100 MVA. So we have to determine the power factor at the generation what it must operate based on the given data. So we have at load A they specify the voltage is 11 kilovolt and then the load is being 50 megawatt at power factor 1, and at bus bar C at point C we have on the load of 200 megawatt at 0.8 power factor lagging, and we have to find out the power factor with respect to generation so that these conditions are being operated. So let's start at load consumer at load A. So at load A they're given as P is equal to 500. So transforming that into per unit, dividing by its base, we get 0.5 per unit. And I'm saying that the Q is 0. Why is Q 0? That's because if not given? No. The power factor is being 1. So as power factor is being 1, so we know that it is pure resistance. For pure resistance, we have only Q, whereas Q is 0. Or as power factor is 1, we get theta as 0, and we know Q is equal to V into I into sine theta. Although they've not given V into I, although we know what is the V at the load side, still we can say since the sine 0 is 0, thus the entire Q goes to reactive power goes to 0. Now, so what we're trying to do here is now we're trying to find the power at load C. So reactance drop in line CA is given as I square into XCA. So we know that V into I, your complex power, is given as P plus JQ, and I is equal to P plus JQ. Substituting this in equation 1, we get that's equal to P square plus Q square by V square into XCA. So here we are in turn finding what is XCA. We know what is P and Q at point C, right? So let's see that. So until now we have found what is find out the value at A. Now between these two, you can see that 0.1 per unit, 0.1 per unit. These two transmission lines they're being parallel. Thus it is 0.1 into 0.1 divided by 0.1 plus 0.1, you get 0.05. And similarly, at this point, we have these two again in parallel. Thus the answer would be again 0.5. Thus the total XCA from A to C is 0.05 plus 0.05, which is 0.1. Now, substituting the value of P and Q is available. So that is P we have calculated as 0.5 and Q as 0. Thus it is 0.025 I per unit. So the reactance drop in line C to A is 0.025 I per unit. Now at bus bar C. So at bus bar C we have transmission line load as well as 200 megawatt. So until point C, right? So at point C we have 200 megawatt divided by 100 base, it's 2 per unit. But what about Q? Is Q 0? No. So we know that power factor is 0.8, and what is theta? Cos units of theta gives us 36.86. Now how do we find the value of Q, as we do not know V at this bus point, right? So we are aware that P is equal to VI cos theta, whether it's single phase or three phase. Similarly, Q is equal to VI sin theta. So now Q by P, we get this as sine by cos, which is nothing but tan theta. We can say that Q by P is equal to tan theta. So we know what is P, we know what is tan, we know what is theta, right? Substitute that and find what is Q. So P by Q is equal to tan theta. Substitute the value of theta and P, we get Q is equal to P into tan theta, and solving this we get the value of Q. So what is P? So P at bus bar C is 2, and until bus bar C, that is from point C to A, it is 0.5. What about Q? So the value of Q is 1.5 is what we have found now, and 0.025 I is what we have found until point C from point A. So what is the power at bus bar P? E. So load at bus bar C plus I square XE power until that is with respect to transmission losses. So now until C we have seen that the total P is 2.5, total Q is 1.525 I. So P and Q is also same. So this is 2.5 to the power square plus 1.25 to the power square divided by 1 square. So this 2 is square superscript and this also is superscript. And now XCE, from C to E we are aware that these two are in parallel. Thus 0.04 and 0.04 are in parallel, 0.1 and 0.1 are again parallel, and these two are in series. Thus solving that we get this term as 0.07. This is 2.5 to the power 2 and 1.525 to the power 2. So solving them, we get the total answer as 2.5 plus 2.125i. Now at bus bar E, the answer is 2.5 plus 2.125i. So converting that into polar form, it is 3.28 at an angle 40.386 degree. And the power factor at point E is nothing but power factor of a generator. Thus it is cos of 40.368 gives us 0.726 lagging. So as you can see, the power factor is 1 at load A and C at point C. Thus the combination of these two will get power factor as lagging power factor at generating. So thank you for watching the video. Please do subscribe the channel to enhance your knowledge further.